Hello everyone, I'm Max Fowler, and on behalf of Dr. John Licato, I am presenting Embracing Inferences Action, a step towards human-level reasoning. And I'd like to start us off with a motivating example, why we are doing this. Let's say we have a robot R that is run using an artificial general intelligence, and it's in a room with its master M and an opponent O. Now R believes that its master is in peril, and it believes that if it says some formula P, it can save its master by inducing a belief of Q in the master's belief set. At the same time, R wants to be careful. The opponent cannot come to believe Q, as that would tip him off and potentially make the situation even worse. At a glance, this seems trivial, but as we approach more realistic situations, we run into problems. For example, the robot R might not have the same belief set as the other two agents. So any reasoning R does to create that P might be missing some key details about the other agent's beliefs. If we assume the beliefs are consistent among all three, we still have no guarantee that the inference rules are consistent between all three. Perhaps R has an incomplete knowledge about M and O's reasoning, or O is an irrational reasoner and will make jumps of logic that no sane person would, making the picking of P much more particular. Even if we assume all of that is consistent, we run into computational issues. Finding a P that implies Q for some belief set isn't too terribly difficult, but showing that P will never imply Q for O's belief set becomes a much more difficult reasoning task. Moving forward, I'll first discuss our solution to that problem, how we can go about preventing O knowing P, or knowing Q rather, which is an extension of the cognitive event calculus. After that, I'll discuss MATR-style reasoning, the type of reasoning and proofing that we're using in our paper and as we develop CECAC in general. And then finally, I'll bring everything together at the end into a wrap-up just to make sure all the ideas coalesce together. So first off, CEC. What is the cognitive event calculus and what is our extension on it? CEC is a first-order modal logic-based extension on Robert Kowalski's original event calculus, which, for those of you not familiar with it, was effectively a logic for representing events and the results of events. CEC adds, again, modal operators, which in this case we're concerned with belief. The idea that an agent, at a certain time, can believe some formula, in this case phi. CCAC is the analogical constructivist variant of cognitive event calculus, which adds a few traits. At a high level, it uses analogical constructivism to allow reasoning via analogies and reasoning over the beliefs of other agents. It also allows for the use of nonclassical logic so that we can approach a more natural human-style reasoning. And I do want to point out that this is an experimental formalism, so everything I'm saying today could be completely false a month from now. We'll find out. So, how do we reach that point where we can try to model that human-level reasoning? We do that in CCAC by having a two-level system. The top level is sort of a system level, and that's more like, if you think about the robot example, that's more of the automatic sensory controls, the basic controls that we use. And at that level, we use ECQ, so the principle of explosion is in effect, as we're using a first-order modal logic. So you don't want to have phi and not phi. If you have phi and not phi at the system level, it can imply any arbitrary formula, and we're in a bad way, robots kill us all, and this talk is meaningless. At the belief level, though, we allow for pair-consistent human-style reasoning, and you can choose any non-classical logic you wish. In this case, we're using CCAC. And that allows us to hold those contradictory beliefs, because humans are capable of holding contradictions. I can believe that I'm at AGI 2016 at the same time that I believe I'm not at AGI 2016. This is just a dream. That's a perfectly valid, if unusual and bizarre, belief state for me. I do want to point out that in the paper it says the system level uses classical logic, and I understand that that's a contention whether first-order modal logic is classical or not, but as it is more classically leaning than what we use at the belief level, we identify it as such here. So, some other traits for CECAC come from Dr. Licato's original analogical constructivism thesis. One of those being the idea of inference as an action. So if we infer a formula, that is to say, we get that belief. And if we want to make that an action, we can use this happens operator here. So it happens at a time that a formula is now believed by an agent. To make this stronger, we put all potential actions that an agent can carry out into an agent's affordance set, which allows us to not only reason about the immediate, but also reason about what beliefs an agent might consider at a future time. And to help with this, we have three forms for our inference rules. The R1 form is a first-person reasoning form, which is typical sort of logical rule construction, and I'll get more into that when we talk about epistemic boxes within MATR. R2 is the automatic normative context of reasoning. I believe it's going to rain. I believe that if it's going to rain, I want an umbrella. Therefore, I believe I want an umbrella. But again, that doesn't match human-style reasoning. I could be incredibly stressed in the morning when it's raining and not consider phi, that I need an umbrella. I could have not slept the night before, and so my reasoning might be muddled, and so I might not believe phi. That's why we have, or psi, that's why we have R3, the affording form for a rule, which changes the bottom to say that it is now an affordance that the agent can infer having an umbrella at time t, or time t1, or time t2, or any time after that t. So it lets us reason not just in the now, but in the future. Now, why is that important? And to understand why that's important, we need to talk a bit about MATR, the Makhno-Arachne tree-based reasoner, which is a joint project between the Analogical Constructivism and Reasoning Lab from my university and the Rensler AI and Reasoning Lab at RPI. MATR, at its basic level, is similar to Fitch-Dow natural deduction using boxes. And I'm not going to read off all of these, instead I'm going to skip to a diagram, but I do want to point out there are two kinds of boxes, a basic proof box and an epistemic box. The proof box, you can see on this closer side, is a typical Fitch-Dow natural deduction for the most part, so I won't dwell on it, but the epistemic box is what's new in this paper. Notice at the top, near the supposition set, which currently holds phi, we have an agent and a time identified. What that means is that within the box's context, we are in A's head at time t. Given that, the reiteration set behaves a little differently than normal. We're allowed to reiterate any formula so long as it is a belief the agent has at that time. So since the agent believes phi implies psi at time t, we can reiterate it into the epistemic box. And when we do that, we switch into more of an R1 form of a rule. Rather than having the modal operators there and getting muddled in that level of reasoning, we just have the phi implies psi, and then a modus ponens, the B standing there is for belief, to get psi. But we're still not done at that point, because that's just the same as a basic Fitch proof. Instead, epistemic boxes can use things called evaluable rules to change the state of a reasoner, to change the state of certain sets. So in this case, we use an implies intro rule, which adds to A that if it is true that A believes phi at time t, it is now an affordance that A can believe psi. Not that he does believe psi, whatever agent A is, but that A can believe psi, again, from time 1 to any time after time 1, as long as nothing were to remove this from his affordance set. From a code standpoint, MATR accomplishes this robust reasoning through the use of codelets. And you can think of MATR in two parts. There's the codelet manager, which creates instances of smaller subprograms called codelets, each of which is designed to perform a specific task to generate a proof. Perhaps we have one that is specifically for, again, belief modus ponens, like we saw in the epistemic box. Or perhaps we have one that's on a first-order logic level and is for double negation. The codelet manager sends these codelets at a list of precedents and conclusion, just asks, what do you think? Is there something you can do to help me solve this? And the codelets will analyze the information and then send back suggestions. So maybe you have a double negation that you could eliminate. Or maybe, like in the epistemic box, you have a clear case of modus ponens. After the codelet manager sends enough of these codelets, each of which is tailored to a specific instance rule or a specific problem, we hopefully find a proof. And if not, MATR crashes because there's probably a logical explosion and you have to close your JVM. But ideally, we get a proof. Now, Another thing about matter is you saw that evaluable rule earlier with the epistemic box. There are two kinds of codelets. There are basic codelets, like the belief modus ponens, like your double negation. And then there's rules called evaluable codelets. And the difference between regular codelets and evaluable codelets is that evaluable codelets can allow for metalogical instructions in your inference rules. So in this instance here, the quoted comment that consistency is a check for, or you can use any sort of code you want there. You don't have to use CCAC, which the rest of this rule is written in. You can use a neural network or another prover, or even ours potentially, to prove that consistency. Given time, I'll go quickly through one of the proofs from the paper, and I won't read each step, but I'll describe what is occurring in each quadrant. So on the top here, the supposition set, we have the robot reasoning about what happens if it says a given P. On the leftward side, we reiterate that happening into the box, and then the robot assumes my master heard P, so my master is going to believe P, and that belief will propagate through time. The robot also takes a bit of an assumption here and assumes that I'm assuming my master has a rule phi. At the area here with the follows, the belief in P and the rule phi come together to say that it is now an affordance for the master to believe Q. But that's not enough to make him believe Q. That just means he can believe Q. For him to believe Q, it needs to be of interest that he believe Q, which is in the top right corner, which gives us the happens that the master infers Q. Finally, because this box is an epistemic box, we use the belief intro, which this large belief statement at the bottom effectively says the robot now believes he has selected the correct P to make his master believe Q. And in the paper, on the other side of the page with this proof, there's a proof for the process of showing that the opponent does not believe Q. That means at the end, we're left with a very happy robot, a master that believes Q and is safe, and an opponent that's confused by the situation and can no longer cause harm. Now, real quick, we'll wrap up with the last minute or so. Again, CCAC is our experimental formalism. The affordance set gives us the ability to reason from this time or in a future time the actions and beliefs an agent can have, which is closer to the way we reason about other humans. And the rule forms let us reason within our head using that R1, or again, in the affordance way with R3, just to give us more options to get closer to human-style reasoning. Matter, meanwhile, gives us strength in the epistemic box benefit, so we can directly affect that belief set using some of those evaluable rules. It's also easily customizable. Those codelets that it's run on, again, you can write any sort of inference rule you wish for those codelets, potentially any sort of logic. You can also interface easily with other systems. Just off the top of my head as an example of that, I know one of the codelets Matter currently has, it uses the Talos online prover, which was also developed by RPI. And in the interest of time, I'm going ahead and cut off there. If you have any questions, feel free to ask during the panel, and if at any point you want to see the state Matter's currently in, I can show you that sometime later during the conference. Thank you.